Volume charge tape. So the purpose of this lab is to look at the behavior of charged pieces of tape and then also calculate the charge on one of the tapes. So to do this, we'll be looking at Coulomb's law. And for a brief preview, we found that the experimental value for the charge of the piece of tape was the same as the coding value, which is 4.7 times 10 to the negative 9 coulombs. And then we also calculated the number of excess electrons and the experimental ratio of deficient electrons to atoms. Okay, so the main equations that we used are one, Coulomb's law, which is, the force due to electrostatic attraction is KQQ over R squared times R. And then the only other force to keep into account was force of gravity. And so the net force is just Fe plus Fg. And the reason that we're doing this is because we can use Coulomb's law and rearrange it to figure out what the magnitude of the charge is. And these are the only two forces that are acting on the tape. We do have a lot of assumptions. Go over these more in depth once we start with the calculations. So for the experiment, we essentially just held a charged piece of tape below another charged piece of tape, and the one on the top lifted up a little bit. So the goal is, charge the two and then measure the distance when this top tape began to float above the second. And, we used a 27-meter length of tape. And so at 1 gram per meter, that goes to around 0.0002 kilograms. Okay, so you can sort of see a little bit, not very clearly, but the piece of tape lifted up a little bit, and that final separation that we saw was about, 1 centimeter. So it's important to note that these were negatively charged, or sorry, the tapes were positively charged, and we knew this because they were attracted to a negatively charged pen. Okay, so the distance, like I mentioned, was 1 centimeter, which is 0.01 meters. And so after that, we also calculated the force of gravity, which is mg. That's shown right there. And then we equated that to the force, the electric force, and rearranged the equation to solve for the charge. And this is our first assumption. We assume that both of the charges are the same. That is, the tapes have the same charge. And so that's where we got this number, 4.7 times 10 to the negative 9 coulombs, which is reasonable because it falls between 10 to the negative 9 and 10 to the negative 7. Okay. We also looked at the number of deficient electrons, which we calculated by taking the charge divided by the elementary charge. That's this number right here. And we used that to look at the ratio of electrons to atoms. And we found that there's a lot more atoms than the electrons that were providing the attraction, or the repulsion, I mean. So to do this, we also kind of looked at a coding model. So uh, started by defining a lot of constants and then writing a function to calculate the E field, depending on one, a source particle and an observer particle. And then using this, you can multiply the E field by the charge to figure out the force of the electric. And you can also figure out the force of gravity by doing mg again. So the net force is force electric on top and force grav on bottom. And so I did this for both of the particles. So that's why you have these 8 lines of code with all the forces. Okay, so then using this code, I essentially just changed the charge until I found the net force on the top particle to be around 0. And so as you can see here, the force, the electrostatic force here is being canceled out by the force of gravity. So the force is very, very close to 0. This isn't quite 0, but it's pretty close. We found this at the same charge, which is 4.7 times 10 to the negative 9 coulombs. Okay, so in both cases, we found that number to be the charge. And this is, again, reasonable because it's between 10 to the negative 7, 10 to the negative 9. And in both cases, we see that Coulomb's law applies. So Fe equals KQQ over R squared, and the net force is just Fe plus Fg. But we did have some key assumptions. In particular, we treated them both like point charges and assumed that they had the same net charge, when this isn't really the case. And so there were some sources of error as well, even though it isn't possible to actually measure the exact amount of charge on the tape. Some sources of error include the tape being handled and losing charge and not being perfectly parallel, some inaccurate measurements surrounding errors, and then all the other forces could have also been at play, such as electrostatic attraction between any other object and the tapes. So if they had a positive, so if you switch the charge of electrons and protons, you would notice that the direction of the E field for the tape would flip, but the actual observations made in the experiment wouldn't, because like charges still repel. So in Coulomb's law, you would just cancel out the negatives in the two charges. And so the reason it's important to not touch the tapes as little as possible is because charge is transferred when you make contact. So to keep the results fair and to maximize the amount of charge, we should avoid touching the tapes with our hands, for instance. So in conclusion, we found the same value of 4.7 times 10 to the negative 9 coulombs, which is pretty reasonable. and we showed that Coulomb's law was a useful way to model the electrostatic force between charged objects. And then we also concluded that the number of deficient electrons in the tape was much smaller than the number of total atoms on the surface of the tape. Thank you.